Doing well. My name is Michael Gianangeli, and I am pleased to introduce Dave Watson and Daniel Rosenheck, who will be presenting the Eagle Has Landed, real-time win probabilities in men's major golf tournaments. Thanks, guys.
Thank you. Do you have a clicker?
Clicker.
Clicker?
Lector in there.
Thank you. All set. Okay, well, thank you all very much for being here. I'm Dan, this is David. We work for The Economist, and we're here to present the Economist Advantage in Golf Likelihood Estimator, which is our system for predicting win probabilities in men's major golf tournaments in real time. So it all started with a very, very bad day for Jordan Spieth in the 2016 Masters. He was up by 5 strokes with 9 holes left to play, and then this happened.
Just let it release. Ooh, that's right. Oh. And that's water. And just like that, 5 shots gone.
Okay,
Good.
so upon that, and he then sent another one into the water after that, I was just curious. It seemed like a pretty spectacular collapse, seemed pretty unusual, but I didn't know. Was 5 strokes in 9 holes really a lot? Was it a little? And so I thought I could just go to the internet, as you could for sports like baseball or football, and just find out what his chances of winning the tournament were. And I Googled around and I didn't really see anything. So it seemed like an opportunity for us to try to find the answer ourselves. Hand over to you.
So we basically had 2 data sets that we kind of cobbled together that was the basis for everything we're going to show you today. For all tournaments going back several years, we've got round level data on how every player did, and including their rank by the official World Golf Ranking System. I don't know what that is. And then for the majors specifically, so that's all non-majors, for the majors we've got hole level data. So that's going to tell you the par, the yardage, and how each player did on that hole rather than just the round level. So slightly more granular there. Now that's not especially wide, but it's very deep. We had a lot of this data. We had about 500,000 player holes for all majors going back to 2001, and we had just about a cool million for actual round level data going back to 2006. Slightly under a million, but we're going to go ahead and call that a million. So with this, what we wanted to do was basically build a model that looks at rank. So here's the rank data itself. And this is actually the first thing we wanted to see was just how reliable are these rankings and how informative are they? They're certainly up to something. This is just showing every player's ranking versus the average scores for players of that ranking. A few things I kind of want to call your attention to. First, that this smooth curve does fit the data quite neatly. But second of all, that the reliability of those rankings does seem to go down a little bit as the rankings enter, especially in like the thousands. So it's quite reliable for very high-ranked players. So this is a classic example of what you'd call heteroscedasticity. The rankings are very reliable at the low end of the range and not so much at the other. Call that gramophone plot for kind of obvious reasons, right? Sort of widens out there. Another sort of central thing to what we wanted to look at, and something that really just emerged from the data, but might also be intuitive if you watch or play golf, is that the hole matters a lot, and especially the par on the hole. So we see very different behavior with different par levels. Specifically, you'll notice that par 5s are the only one we don't fit a linear model to for distance. And that's because par 5s, which are about 1/6 of holes, make up 1/3 of birdies. So the distance is a really big variable here. The hardest holes are going to be the really, really long par 5s, but slightly shorter par 5s are where a player can really make up a lot of strokes with their birdies and eagles. They're very overrepresented there, as we see. Par 4s are the majority of data. This is, 63% of all holes. But there is a good range here of distances and difficulties, and you can see that that linear fit to that is actually quite neat. Par 3s can be very, very short, which means that it's very hard to get a birdie on those, right? You need to basically, eagles, you need to get a hole in one, and birdies, you need to shave one stroke off this already very short distance. So everything we do in the model, we do individually at each par level. We've split up basically everything at that level. Now, you add up everything we have there with the rankings, the pars, and the distances, and you can actually get a pretty decent model running for these player projections. So to just highlight some extreme examples, so the best and worst projections on any particular major hole we had. You got Tiger Woods here in the 2002 British Open, who had a projected score-to-par average of negative .472, and he actually outperformed that. He had 1 birdie, 1 eagle, 2 pars for an average of negative .75. On the other extreme, we had the world's 1,599th player in the 2015 US Open, Jimmy Gunn, who had the worst projected score to par, almost a bogey, .711, and he did, in fact, go on to bogey that hole. So this range is actually quite wide, as you can see we get with these projections. Now, the rank data from the OWGR is fairly reliable, as I showed you before, but it's also got its limitations, especially for a predictive measure, which is what we're really looking for here. So it's by definition backward looking, right? It's going to be a measure of how the person performed in especially their most recent tournaments, and it's going to rely on recency, but also, you know, how did everyone else play, right? So for instance, to take one sort of recent example, Phil Mickelson had an amazing 2016 British Open, really one of the finer performances of his career, but he didn't win because the field was just incredibly difficult that day, and this can happen at either end of the extreme, right? So we believed that the rankings would underrate him in that case. So we want a skill measure that's not going to rely just on rankings, but can take that information and then hopefully add a little bit more to it. So how can we level the playing field? Well, we have this immense amount of data from round level, right? This is the non-major data that we wanted to incorporate in. And because it's at a different level of granularity, it wasn't always so obvious to see how we could get these to sort of talk to each other. These tournaments are also very different kinds of tournaments, very different range of players and rankings that are going to be on them, and very different sorts of courses that they're playing. So we need to get a way to get all this data sort of on one par, to use that sort of term. We can't, at least with any of the data that we are including here, measure course difficulty directly. We can't incorporate any information on, you know, whether there are lakes or roughs or anything like that. So we need some other way to try and get this from what we do have, unobserved difficulty. So for majors, we infer how hard a course was from the player performances themselves directly, because we have these projections, right? And then we have how the player actually did. So we want to basically look at the differential, the gap between observed and expected performance. So on every level, we do this for the rounds, and then for the majors themselves, we can do it at the level of the holes. So to again pick out some extreme values on either end of the spectrum here, the easiest by this method is at Baltusrol, I'm not sure I'm pronouncing that right. The PGA Championship in 2016, we saw that the gap between observed and expected score to par was negative .095, which is, you know, just about a tenth of a stroke. The hardest would be Royal St. George British Open in 2003, where you had this .195, a full 2/10 of a stroke gap between observed and expected. So we're taking this as sort of a proxy for the difficulty of that hole. It seems to indicate...
Of the course.
Of the course, right. It seems to indicate that that particular course, either through weather or design, was playing especially difficult in that tournament. That basic idea of looking at differentials between observed and expected outcomes, we're also going to go ahead and apply to the whole level data. So the only direct level, right, the only direct observations we have really here are par and distance, so we're not going to know things about slopes and hazards, which would obviously be helpful. Now, to take an extreme example, the 18th hole at St. Andrews, which is named after Tom Morris, is a short par 4. It plays very easily. Everyone does quite well on this hole in the data. You can see about 40% of people go on to birdie that hole. But for every Tom Morris, you've got, for instance, the 14th hole at Pebble Beach. Now, so this is actually a really nice validation of what we were doing with our model. we saw, just as that this hole was coming out as an outlier, and I, anyway, didn't know anything about Pebble Beach's 14th hole. This didn't mean much to me. But a quick Google around showed articles like this one, that this has been flagged as a hole where people are performing it's an especially challenging hole. And to walk you through what that really means, so it's a 580-yard par 5, which puts it sort of on the longer range, right? But this is the spread of score outcomes that we find on an average 580-yard par 5, according to the model, and then what we actually find on Pebble Beach. And the sort of point I want to draw your attention to here is the basically just flip between birdies and bogeys here. It's about 3 times as likely to birdie as you are to bogey on an average 580-yard par 5, and it's the exact opposite here. You're about 3 times as likely to bogey as you are to birdie.
Indeed. So now for the non-majors, we did not have this level of granularity. We wanted to use every recognized tournament on the planet for the past 10 years, and all we had for that was round scores and world rankings. However, we had so many observations that we were able to still extract some very valuable information from it. So to give you a sense of how we did this, let's take 2 tournaments. We have the 2006 Nedbank Golf Challenge and the 2015 Wealth Design Invitational. In the first, Ernie Els shot 1.33 strokes higher, that is to say worse, than the field average. In the second, Darren Lloyd shot nearly 2 strokes better than average. So we would assume that Lloyd had outperformed Els on that day. However, the field average isn't always just average. South Africa's Nedbank Challenge isn't necessarily a tournament that I knew of, but pro golfers certainly did because it had the highest prize in the entire sport at that time. By contrast, the Wealth Design Invitational is a much more modest event. So, in fact, the Nedbank Golf Challenge is so strong, it was actually stronger than a major. 11 of its 12 entrants were in the world's top 20. We would expect that the average player in that tournament would actually shoot just 1 stroke over par in a major, which is better than the observed average in majors, whereas the WDI average player in WI would be far, far worse. So with these differentials, this is basically like a Rosetta Stone. As we can use these projections to put tournaments of very different difficulty levels or different skill levels on a level playing field, simply by taking your score above average and then adding on how we think the average player in that tournament would have done in a major. So to give you a little work through, using the same 2 players, Ernie Els was in a tournament where the average player would be 1 stroke above par in a major. He was 1 stroke above that, so we think he would have been about plus 2.4 in a major relative to par. By contrast, Lloyd was in a tournament where we think the average player would have been 6 strokes over. He was 2 strokes better than that. That comes out to plus 4. So we actually think that Els had a better day by 1.77 strokes, even though he did worse relative to the field average. With this information, we can blend the majors and non-majors and try to predict forward into the future. We developed and used this equation, which we've designed to look as terrifying as possible. But really, it's just a weighted average. So it's a weighted average of 2 things. On one side, we have your rank and the score we would associate with that. And the other, all these squiggly Greek letters, are just taking a weighted average, a time-weighted average of your past performance in every tournament we have for you, adjusted for the strength of the field. We solve for parameters that give us the best fit, and we're just sharing the numbers with you there. I won't actually walk you through this entire worked example, which doesn't look easy, but trust me, it is. But it's simple childhood arithmetic to say a tournament from 30 days ago, you were 6 strokes above par or below par. Therefore, we associate that with this score. Rinse, lather, repeat, and you wind up with a projection for everything. Now, there's some assumptions baked into this approach that we now need to question or challenge. The first is that all of these calculations treat every context-adjusted score the same. That would be true if golfers were all robots. In fact, different golfers are different people. Some are better at driving, some at putting, some play well under difficult conditions, some don't. So once again, we can use the volume of our data to try to get player-specific information. So for example, let's take Luke Donald. He's a former world #1 and he's been PGA Player of the Year, but he's a fairly modest driver. We would expect that somebody who doesn't have much of a long game would have more trouble relative to his own average on long holes and would do better relative to his own average on short holes. And sure enough, that's exactly what we find. After adjusting each hole for its distance relative to its par value, you can see we have plotted 2 lines through this data. The average player has one slope and Donald has a steeper slope. So because he's good at golf, he's still better than average at every distance level. But for short holes, he's way better than average, 0.115 strokes better than average, whereas for a long hole, he's only slightly better than average. Take it over.
So everything that we've just sort of talked about is projecting toward the mean, right? Trying to find the central tendency of how all these people are going to perform. But one thing that became pretty obvious, especially when we're turning these discrete hole scores into averages that are going to pretend that they're continuous, is that mean is really only part of the story. There's actually other factors to this distribution that are worth modeling as well. So these are the higher moments, we might say. So to generate these accurate predictions, we're going to need to find the extreme parts of this distribution as well, not just at the center. So to do that, we're going to need to model, for instance, the variance. This is the second moment of the distribution. That's going to tell you how spread these values are rather than just where they fall in the middle. But we didn't stop there. We also modeled the skewness, which is the third moment. The skewness is indicating not just the spread and the central tendency, but where that central tendency, where the mass is going to fall in that distribution. We got negative and positive skews. So also, obviously, we should note that in golf, no one's really going to go much better than an eagle. I think we had 1 or 2 examples in the data. Albatrosses. But you could have no upper bound potentially on the skew of a distribution. And we also modeled the kurtosis. So the kurtosis is the next higher moment. And in this particular context, you can think of this basically as a measure of the uniformity of this distribution. If it's very flat, if it's got a negative kurtosis, that means all the sort of possible outcomes are roughly as likely as each other. This is especially valuable for holes that have wide ranges of outcomes, and we do see a lot of these in the data. So to take one example, the 16th hole at Hazeltine in Minnesota, it's a shortish par 4, it's about 402 yards. But what that isn't telling you is about all the potential hazards that we find on this hole. So you've got a pretty large lake, there's streamlines, the wind can be really devastating sometimes, but sometimes not. So luck becomes a really major factor here, and if you're fortunate enough to be there on a sunny day, you could very easily get a par, maybe even a birdie if you had a nice putt. But if you're less fortunate, it's not that unusual to find lots of these 2-stroke penalties adding up and some really extreme outcomes on this hole. To sort of put some numbers on that, we see that the average 402-yard par 4, which Hazeltine is, as I said, not very average, about a little more than a third of all outcomes are going to be non-par outcomes for that hole. But at Hazeltine, 46% are non-par outcomes. So we see that there are extreme values coming up on this kind of hole, and we see a lot of that in the data. Moving from sort of hole level to player level, we also see a lot of variability in these higher moments for players. So some players are very consistent, very reliable pars, and this comes down a lot to your style of play. I think this is a big difference between big drivers and big putters. To take a famous example, we've got Jim Furyk here, right? So Jim Furyk, who's pictured here like having a heart attack or something, he has 64% of his shots are par, which is actually a really remarkable level of consistency. And he's known as a very reliable putter, and the data really does bear this out. Then you've got some people who sort of fall on the other side of this distribution. So the least consistent player in the data. Jim Furyk did come out as the most consistent, by the way. That's not just conventional wisdom. That's actually what the numbers suggested. The least consistent player in the data is someone you might have heard of. It's this guy, so Long John Daly. He's got a well-deserved reputation as a volatile performer in lots of different respects. And in majors, he averaged a score of at least 2 strokes away from par in either direction once for every 16.6 holes, which is more than once around, and that's extremely unusual. He's either great or not. And so to sort of visualize this, I actually think this plot really puts this into perspective here. So we mean-centered their distributions and plotted their daily scores. And what you can see, basically, the orangish red curve is Furyk, and the blue one is daily. That Furyk's probability mass is a lot higher toward the center, whereas John Daly is much more blown out around the tails. And this is the sort of thing that, they may, as a matter of fact, they don't have the same mean performance, but you could imagine that they actually might in this scenario, and you'd be missing a lot if you were only modeling the mean, because there's actually all this variance that you're not getting here.
I'll take over from here. So another assumption that's been baked into everything we've done so far is we're modeling these scores as continuous distributions to 3 decimal places. That is not actually how things work in real life, where there's no such thing as a fractional stroke. So to predict the discrete scores that actually occur in golf, we took our forecast for all these 4 moments for both players and holes into what's called a Cumulative Probit model. And with that, we can then now see how each of these forecasts translate into whole probability outcomes. So first, starting on par 3s, we've got the best player in the world and the worst that we saw on a short par 3. As you can see, there's really not that much difference. A short par 3 is basically a putting contest. The main thing that separates good golfers from not so good ones is their long game. So the only difference between Tiger Woods and Michael Weaver on a short par 3 is about 5 percentage points of probability between birdie and bogey. On a very long par 3, nobody's ever going to birdie it, but if you're a superstar golfer like Jason Day, you can make or beat par pretty consistently, whereas if you are a lesser golfer, you're going to bogey more often than not. For par 4s, the most common hole, we see bigger spread. Still, obviously, for a very short par 4, that's par 3 distance, you're going to see a lot of birdies, but you need an approach shot, and that gives more opportunities for players to distinguish themselves. So Tiger Woods here is about 10 percentage points more likely to birdie than Michael Weaver would be. On a long par 4, you start seeing enormous differences. So again, because it's so long, even the greatest players in the world are going to bogey frequently. Rory McIlroy would be about 30%, but he still has an 8% shot at a birdie despite the length of the hole, whereas somebody named Cole Hammer is going to fail to make par 2/3 of the time and actually has a 15% chance at a double bogey or worse. And finally, on par 5s, short par 5s are by far the easiest holes, and as you can see here, on a short par 5, Tiger Woods is actually 6% to get an eagle, which is incredibly unusual, and 60% to beat par. And even a 69-year-old Billy Casper at the Masters, the hole is just so short for its par value that you can make it in 5 strokes, and he did. Conversely, at the very long end of the spectrum, 684 yards is really longer than anyone is sort of trained to prepare to hit for. But if you're Jason Day, you can still, again, make par the most of the time and have a shot at a bogey, whereas if your name is Derek Chang, you're about 60% for a bogey or worse. So the absolute best projected outcome we have is Tiger Woods on a short par 5, 7% for an eagle, 58% for a birdie. And the worst single projection in our data set was for a guy named Laurie Cantor at the 2010 British Open, which was not only an unranked player on a long par 5, but it was a hole that was playing super difficult. Half of the previous shots on the hole were bogeys or worse. So we projected a 75% chance that he would miss par, and sure enough, he double bogeyed. So now we have, for each hole, we have the hole that had the highest probability of that outcome. So the highest chance of an eagle was Phil Mickelson on a very short par 5 playing easy. Highest chance of a birdie was Tiger Woods on the exact same hole. So 7% eagle is the highest, 58% of birdie is the highest. Now the highest odds of a par is going to be on a par 3, where scores tend to be much more tightly crunched together. And this is a steady golfer, Henrik Stenson, on a low variance par 3, 76% chance of a par. Moving on to the worst performances, when you have an unranked player on a super long par 3, that's a 53% chance of a bogey. When you have an unranked player on a super long par 4, that's a 20% chance of a double bogey. And to get really meaningful odds of a triple or quadruple bogey, you need to be on hole 14 at Pebble Beach. Every single hole player hole with greater than a 5% chance of a triple bogey was on that hole. Finally, all these probabilities are at the hole level. We need to aggregate these up to see who's actually going to win. For this, we used the Monte Carlo simulation technique. Using all these probabilities, we ran every major 10,000 times, repeated after every hole since 2001. And very importantly, we ran these simulations dynamically. So if a guy happens to, in one simulation, randomly start off doing really well, we're going to improve his projections the rest of the way, and vice versa. So this reflects the way these things actually evolve in real life. This wound up requiring some computational power. That's 100 rented Amazon CPUs going at full blast. It took some time to get through it, but we made it happen. And then we had a real moment of truth. We'd gone to all this effort to model this. But was it going to work? Did our simulator actually produce accurate win probabilities? Well, we had a probability for every player after every hole, and we knew whether they won. We went to count it up, and bingo. This graph shows our projected probability of victory for each player after each hole and how often they actually won, and it's basically a straight line. So we started with Jordan Spieth. Let's end there. Just how improbable was his collapse? Pretty unlikely. We had about a 96% chance to win that, and then crashed. It was not, however, the single worst collapse in our data set. That belonged to Adam Scott, who led the 2012 British Open by 4 strokes with just 4 holes to play. Then, the next hole, he bogeyed. The next hole, he bogeyed. The next hole, he bogeyed. And the last hole, you can guess, he bogeyed. And that is his win percentage falling off a cliff. Conversely, we saw some incredible comebacks. We run 10,000 simulations precisely, so even the most improbable outcomes we can assign a number to. Sometimes the gods of golf will throw you something so unlikely that you couldn't even model it. In the 2009 PGA Championship, Tiger Woods was 8 under by the 34th hole. He had a big lead in the 3rd round. He already had a 70% chance to win. He could certainly be beaten, but it certainly wasn't going to be by Y.E. Yang, who was 110th in the world and had 1 year on the PGA Tour. He trailed Woods by 7 strokes after 39 holes. We ran 10,000 simulations at that point, and Yang won none of them. But then, Woods shot 3 over the rest of the way. Yang went 7 under in the final 2 rounds and won by 3 strokes. And as you can see, he's at the 0 line he's at the x-axis of that graph until almost the very end. So that's what we've got. Thank you all very much for your time and interest, and we look forward to your questions. Oh, that's it, okay. You gotta turn it over. All right, thank you very much.